If s of t equals 2t cubed represents the position of an object as a function of time, find the corresponding velocity and acceleration functions. Now remember that if we have a position function, the velocity is the derivative, the first derivative, and the acceleration is the second derivative. So we're basically being asked to find the first and second derivatives here. It's just that we have motion as some context. So let's try to start with the velocity function. The velocity is going to be the derivative of the position function. So that's going to be the limit as h approaches 0 of s of t plus h minus f of t all over h. So this is going to be the limit as h approaches 0 of 2 times t plus h cubed minus 2t cubed all over h. So there's some algebra that happens there, but we have already worked with the cube of a binomial multiple times. T plus h cubed is going to be t cubed plus 3t squared h plus 3th squared plus h cubed. We've got to multiply all of that by 2. So this is going to be 2t cubed plus 6t squared h plus 6th squared plus 2h cubed. And then we still have minus 2t cubed all over h. We can cancel the positive and negative 2t cubes. And then each of the rest of those terms are divisible by h. So I want to go through and divide each of them by h. 6t squared h divided by h is going to be 6t squared. And then plus 6th squared divided by h is going to be 6th. And then plus 2h squared, h cubed divided by h is h squared. And if we look at the limit as h approaches 0, the second and third terms vanish, and we're just left with 6t squared. So the velocity function is going to be 6t squared. That is the first part of the problem. But then we need to find the acceleration function. And the acceleration is either the second derivative of position or, equivalently, the first derivative of velocity. Because the second derivative is going to be the derivative of the derivative. So we've already got the first derivative. We need to differentiate that to find the second derivative. So this is going to be the limit as h approaches 0 of the velocity function at t plus h minus the velocity at t all over h. All right, so we've got the limit as h approaches 0 of, well, the velocity of t plus h is going to be 6 times t plus h squared minus 6t squared all over h. We need to expand this. So that's going to be 6t squared plus 12th plus 6h squared minus 6t squared all over h. We've got our fun cancellation game to work out. 6t squared minus 6t squared is 0, so those go away. The other two terms have h's in them, so we can do that division. And this gives us the limit as h approaches 0 of 12th divided by h is 12t plus 6h squared divided by h is going to be 6h. And if we take the limit as h goes to 0, that second term vanishes and we're left with 12t. So the acceleration function is equal to 12t. And we're good to go.